Okay, so section 16.8 is going to cover what is called Stokes' theorem. And then section 16.9, which is the last section we will do, covers what's called the divergence theorem. So all we're talking about today is what's called Stokes' theorem. Stokes' theorem should remind you a little bit of Green's theorem. So if we're going to start with Green's theorem, if you recall, that symbol is a line integral that is closed with positive orientation. And if we were taking that line integral of f dot dr, which is work, Green's theorem tells us that we can change this into a double integral over the region R of partial of q with respect to x, subtract partial of p with respect to y, dA. So if you remember, this is Green's theorem. Green's theorem, we have to have a closed curve, and that curve is on the xy plane. So if you remember, both q and p are functions of x and y. And this symbol means that we have a line integral with positive orientation. Okay, so one thing that we talked about when we did Green's theorem, well, it was actually the section after Green's theorem, we talked about how you can take that f dot dr, or Green's theorem, and you can actually write that as a double integral that involves curl. So curl of f dot k dA. And so as a quick review, the question was, why are we allowed to do that? So if we start by finding curl of f, we are crossing the gradient. So partial with respect to x, partial with respect to y, and partial with respect to z with f, which is p, q, 0. Remember, again, p is a function of x and y, q is a function of x and y, and then we're on the xy plane, so there is no k component. Okay, so finding our I, we get the partial of y with respect to 0, which is just 0. Partial with respect to z of q. Q is a function, though, of x and y, so there is no z, so that gives us 0. Same idea for j. We get 0 minus, again, 0. And then for k, we get the partial of q with respect to x, subtract the partial of p with respect to y. So then what we're doing is we are taking that curl, which we just found, and we are dotting it with k, and k is 0, 0, 1. And you should see that gives us our Green's theorem from above. So that gives us the Green's theorem from above. It's just written in a different manner. So what that's leading us to is that Green's theorem can be tied to curl. Now, Green's theorem, though, like we said above, only works for a curve that is on the xy plane. So what do we do if we have a curve that is not on the xy plane? That's what we're going to look at now. So what's new today is we are looking at a similar idea, but in 3 space. So let's say that we have some type of figure like this. And it's moving that way. So So with Green's theorem, we have to have a positive orientation. If you remember from the Green's theorem video that you watched, positive orientation relates to the right-hand rule. Positive orientation for a surface also relates to the right-hand rule. So right-hand rule, when you use your right hand, the surface has to be on your left. Surface being on your left will give positive orientation. Orientation is either going to be up or down. So we have to figure out, is this going to be oriented upwards or downwards? If you picture having your right hand and moving it along the curve, following the orientation that it has, that tells you that this is oriented upwards. Okay, so this relates to Stokes' theorem, or it leads us to Stokes' theorem. Here's what Stokes' theorem says. Let S be an oriented, piecewise, smooth surface bounded by a curve C with positive orientation. And here's what Stokes' theorem says. The line integral of f dot dr can also be calculated as the surface integral of curl of f dot ds. Everything we're going to do today is just related to this theorem. Can I keep going?
Is the ds a capital S or lowercase?
Capital. And with the surface integral, it will always be capital. Okay, here's our first example. Let's take f of xyz to be x squared, 4xy cubed, and xy squared. And we are going to find the work done by F on a particle traversing z equals y as shown. So this is the part of the plane that I'm talking about. And then that's our orientation. So obviously we know we're going to use Stokes' theorem. Before we talk about why we're going to use Stokes' theorem, I want us to talk about how we would have done this problem 10 minutes ago, before we learned Stokes' theorem. So, first of all, with work, it's going to be the line integral of f dot dr. So, for any line integral, first option is you can use Green's theorem if your curve is on the xy plane. So, in our case, that doesn't apply. Our curve is not on the xy plane. So instead, what we would have had to do is we would have had to parameterize all 4 lines and set up 4 separate line integrals. So we would have had the line integral of the first line, then we would have had line integral of the second one, so on and so forth up until the 4th one. So obviously we don't want to do 4 separate line integrals. We don't want to have to parameterize all 4 of those lines. So the question is, can we use Stokes' theorem? Okay, so first of all, the surface has to be smooth, which we have. Then we have to have a curve with positive orientation. So we have to figure out what positive orientation means in this case. Again, you're using the right-hand rule. So picture your right hand traveling around the curve, and you need to make sure that you keep the curve to your left. It's going to be the opposite of the first example we looked at, where this will be our positive orientation. So yes, we can make that happen if n is down. If we remember from the last set of notes, finding n when our surface is oriented downward, if you remember, there were 3 components. Last one means down means that the last component is -1, and then we have positive z of x, positive z of y. So that's how we're going to find our n eventually. We're not going to do it yet. Okay, so our work then, instead of using this line integral, we can calculate it as surface integral of curl of f dot ds. So let's find our curl of f. So it's the gradient, which is the partial with respect to x, partial with respect to y, and partial with respect to z of f. And f is x squared, 4xy cubed, xy squared, so if we find the I component, we get 2xy minus 0, which gives us 2xy. For the j component, we get y squared minus 0, but then we have to flip the sign. And for the k component, we get 4y cubed minus 0, or 4y cubed. So then, this is going to become the double integral over the region R of that curl of f, so that 2xy negative y squared 4y cubed dotted with n. Dotted with n. Keeping in mind that our surface is z equals y. So the partial with respect to x is going to be 0. Partial with respect to y is 1, and then we have a negative 1. So then that would become negative y squared minus 4y cubed. Our region, thankfully, is rectangular, so I'm going to integrate with respect to y first and then x. Y goes from 0 to 3, and x goes from 0 to 1. And if you trust me, I will tell you, you get an answer of negative 90. Questions before we look at another one? Okay. Let's try another one. Evaluate the line integral of f dot dr, where f of x, y, z is equal to negative y squared I plus xj add z squared k. And C is the curve of intersection of y plus z equals 2 and x squared plus y squared equals 1. We are going to orient C to be counterclockwise when viewed from above. Okay, so of course the first thing that we're going to have to do is we're going to have to draw a picture to figure out what this curve is. Okay, x squared plus y squared equals 1. We should be able to tell is going to be a cylinder. And then y plus z equals 2 is a plane. So we have our cylinder coming up, but then it gets cut off by this plane. Okay, so our curve C then is right here. So that is our curve C. And we are told that it's oriented counterclockwise when viewed from above. So that would be here and there. Okay, so here's the thought process that we need to go through. To use Stokes, do we have a smooth surface? Yes, we do. Do we have a curve with positive orientation? Well, using the right-hand rule, figuring out where our n would be going up. So that's the positive orientation that we're going to use. Okay, so then it's going to be negative z of x, negative z of y, and positive 1, eventually when we get to the point of calculating that. Okay, so both of those are met. That tells us we can use Stokes' theorem. So that's what we're going to do. Again, you're going to start by finding the curl of f. Crossing the gradient with f. Okay, so finding the I component, we get 0, subtract 0. Finding the j component, we get 0, subtract 0 again. Finding the k component, we get 1 minus negative 2y, or 1 plus 2y. Finding our n. Our n is going to be based off of our z surface. So if we take that y plus z equals 2, that tells us that z equals 2 minus y. So our n then will be 0, 1, 1. So now we're ready to evaluate. We have that line integral of f dot dr. That's what we want to evaluate. This is going to become a double integral of curl of f, so 0, 0, 1 plus 2y, dotted with 0, 1, 1. It's going to become double integral of 1 plus 2y. So then figuring out where our region R is. Our region R is the region in the XY plane. So it's going to be that circle, which tells us we should probably convert to polar. So this becomes 1 plus 2r sine of theta, r dr d theta. R goes from 0 to 1, theta goes from 0 to 2 pi. And you all have calculated so many double integrals at this point, we're not actually going to do the calculation. I'm just going to tell you that it ends up being pi. Okay. Questions before we keep going? I don't think that Stokes' theorem is incredibly complicated. What is most difficult, in my opinion, is you can tell from Stokes' theorem it equates a line integral with a surface integral. So it is going to be up to you to determine when it is more appropriate to use a line integral versus a surface integral. Sometimes it's going to be easier to use Stokes' theorem. Sometimes it'll be easier just to treat it like a normal line integral. So we have 2 examples we're going to look at, and then we will be done. Okay, so Green's theorem versus Stokes' theorem. Green's theorem takes that closed integral, line integral of f dot dr, and it turns us into a double integral of partial of q with respect to x, subtract partial of p with respect to y dA. Okay, so that's Green's theorem. That is just a special case of Stokes' theorem. That's what we talked about on the first page. So Green's theorem is just a special case of Stokes' theorem. Okay, third example. We are going to verify Stokes' theorem for f of xyz is equal to 2z, comma 3x, comma 5y, where s is the surface z equals 4 minus x squared minus y squared, and z is greater than or equal to 0, with upward orientation and c is the curve x squared plus y squared equals 4 on the xy plane with positive orientation. Okay, so starting with a picture. Z equals 4 minus x squared minus y squared. It's a paraboloid opening down. It has a z-intercept at 2. Nope, I lied, at 4. So this is what we're looking at. So this upper part right here is our surface, and it has upward orientation. And then we are also told that our curve is this circle, x squared plus y squared equals 4, with positive orientation. So positive orientation meaning that using our right hand rule, when we put our right hand up, the surface is going to be on our left. Okay, so first thing we are going to do is we are going to calculate the line integral. So to do that, we are going to have to orient that curve, that red curve. It's a circle, so that gives us 2 cosine of t, 2 sine of t, and 0. So that's going to give us the integral of f of r. So we're going to have to take r and plug it into f. So 2z, or 2 times 0 is 0. 3 times x, so 3 times 2 cosine t gives us 6 cosine t. And then 5y will give us 10 sine of t. And then if you remember, we dot that with r prime of t, which is going to give us negative 2 sine of t, 2 cosine of t, and 0. So again, this first one is just f of r, and the second one is r prime of t. It's one of the first ways we learn to calculate a line integral. When we multiply that out, we end up getting 12 cosine squared of t dt, and t goes from 0 to 2 pi. Okay, we're not going to calculate it. I will just tell you it's 12 pi. So that is the computation of the line integral. What we are now going to do is we are going to calculate the surface integral using Stokes' theorem. So we're going to start by finding the curl of f. So our f was 2z, 3x, and 5y. So we get 5 subtract 3, which is just 5. And then we get 0 subtract 2, but change the sign. Then we get 3 minus 0. So then we said that S has upward orientation. Or that's the positive orientation, which tells us then that our n is going to be negative z of x, negative z of y, and 1. And z is that 4 minus x squared minus y squared. So we're going to get 2x, comma 2y, comma 1. So then, if we want the surface integral of curl of f dot ds, it's going to become the double integral of curl of f, so 5, 2, 3, dotted with n, so 2x, 2y, 1, dA. Which becomes 10x, add 4y, add 3, dA. And of course, our region R is just that circle in the xy plane. So we're going to want to convert to polar. So this will be 10r cosine theta plus 4r sine of theta. Add 3, r dr d theta. Circle has a radius from 0 to 2, and theta goes from 0 to 2 pi. And believe it or not, this would give us an answer of 12 pi. So I would argue in this case, the line integral was significantly quicker. And if we would have recognized that, I mean, we had to do both because that's what the problem asked us. But if we would recognize that in the homework, that it'd be easier to do the line integral, it's going to be a lot shorter. We have one last example to do. Questions before the last example? Okay. This last example, we are specifically doing so that we can decide what is going to be quicker, a surface integral or a line integral. We are calculating the surface integral of curl of f dot ds. F is xz, comma yz, comma xy. S is the part of the sphere, x squared plus y squared plus z squared equals 4, that lies inside x squared plus y squared equals 1 and above the xy plane. Okay, so let's draw ourselves a picture. Okay, so if we're above the xy plane, then we're only looking at a hemisphere. We have that part of the hemisphere. But then we have x squared plus y squared equals 1. Okay, so we have to figure out what our S is. S is the part of the sphere that lies inside the cylinder and above the xy plane. So S is going to be this stuff right here. Okay, so if we try to calculate the surface integral, this is an oriented surface, we would have to find n. Problem with finding n is we do not have an easy equation for z. So if we wanted to find n, we would have to use this equation, and we would have to solve for z to find the vector for our orientation. We don't want to do that. That's not going to be efficient at all. So instead of calculating this as a surface integral, we're going to calculate it as a line integral. This is our C. It's the intersection of our two surfaces. So we're going to calculate this as a line integral instead. To do that, we're going to need to find C. So we start with x squared plus y squared plus z squared equals 4. We also know that from our other equation, though, x squared plus y squared equals 1. Substituting that in, it gives us z squared equals 3. So we're looking at the circle, x squared plus y squared equals 1. Positioned at z equals root 3. So we are going to treat this as a line integral. Our r of t, based off of that circle that we just found, is cosine of t, comma sine of t, comma root 3, which means our r prime of t then is negative sine of t, cosine of t, 0. So then, surface integral of curl of f dot ds. Stokes' theorem tells us that we can do this as a line integral of f dot dr. Okay, so we're going to take f of r. So that's going to be root 3 cosine of t, root 3 sine of t, cosine of t, sine of t, dotted with r prime of t. So that's negative sine of t, cosine of t, and 0 dt. T is going to go from 0 to 2 pi. If we multiply this out, we get negative root 3 cosine of t sine of t plus root 3 sine of t cosine of t plus 0 dt, which is just 0. Which is just 0. So, again, on your homework, you're going to have to be able to determine which one is quicker. Is it quicker for me to use a surface integral or a line integral?